Section 1.7, Deductive Structure by Kieran Beckham. The objectives of this section are to be able to recognize that geometry is based on a deductive structure, identify undefined terms, postulates, and definitions, and understand the characteristics of theorems and the ways in which they can be used in proofs. The structure of geometry. You have just spent a few days writing the two-column proofs and paragraph proofs. Since you have learned how to prove a few statements, you may be interested in knowing something about the theory of proofs. So geometry is based on a deductive structure, which is a system of thought in which conclusions are justified by the means of previously assumed or proved statements. Every deductive structure contains the following four elements: undefined terms, assumptions known as postulates, definitions, theorems, and other conclusions. Undefined terms, postulates, and definitions. These form the foundation on which the rest of a deductive structure is based. Some examples of undefined terms are like points and lines, which we already know about. Although we have not defined these terms, we have described points and lines so that everyone should have a fairly clear idea of what they are. As yet, we have not formally presented any postulates. We have, however, used some algebraic postulates in solving problems. A postulate is an unproved assumption. A definition states the meaning of a term or idea. In this book, important definitions are being identified by the heading definition, like above. One very important characteristic of definitions is that they are reversible. For example, the definition of a midpoint can be expressed in either of the two ways. If a point is the midpoint of a segment, then it divides the segment into two congruent segments, and it can be stated the opposite way around too. In some problems, form 1 of the definition of a midpoint must be used. In other problems, the definition must be reversed, as in form 2 above. Notice that the definition is stated in the form if P, then Q, where P and Q are declarative statements. Such sentence is called a conditional statement or an implication. The if part of the sentence is called the hypothesis. The then is the conclusion. If P, then Q can be symbolized as P arrow pointing to Q. The converse of P, if P, then Q, is if Q, then P. To write the converse of a conditional if-then statements, you reverse part P and Q. Converse of if P, then Q is if Q, then P. So forms 1 and 2 of the definition of the midpoint are converses. As you have seen, a theorem is a mathematical statement that can be proved. Almost all theorems will be numbered in the book. Each theorem will be preceded by a heading such as the following: Theorem 78. Theorems and postulates are not always reversible. For example, if two angles are right angles, then they are congruent is true. The converse statement, if two angles are congruent, then they are right angles, is not true. Remember, definitions are always reversible. Theorems and postulates, however, are not always reversible. It is important to pay attention to the direction of the flow of logic in order to avoid this error. The theorem, if two angles are right angles, then they are congruent, means that whenever we encounter right angles, we can conclude that they are congruent. This is the flow. Input, then conditional to the output. Here's our problem. State the converse of each of the following statements and tell whether the converse is true or false. If an angle contains 90 degrees, it is a right angle. The converse to this statement would be if Q, then P. So it would be if an angle is a right angle, it contains 90 degrees, which is true. For number B, or letter B, if Mary received a B on her history test, then she passed the test. The converse of this statement would be if Mary passed her history test, she received a B on the test, which is false because she could have received an A to pass.
Section 1.8. The objective of this section is to recognize conditional statements, recognize the negation of a statement, recognize the converse, the inverse, and the contrapositive of a statement, and use the chain rule to draw conclusions. In this section, we will review and extend the discussion of conditional statements used in section 1.7. We will use it in the form if and then. A declarative sentence can be two straight angles are congruent. The conditional form are if two angles are straight angles, and then they are congruent. We need to remember that the clause following the word if is called the hypothesis. The clause following the word then is called the conclusion. The conditional statement if P then Q can be written in symbols as P arrow Q. The negation of any statement P is a statement not P. Thus, the negation of it is raining is it is not raining. The symbol for not P is that in P. Notice that the negation of it is not raining is it is raining. In general, not P is equal to P, or not P is equal to P. Every conditional statement, if P then Q, has three other statements associated with it. We have already been introduced to the first of these, the converse. There's the converse, which is if Q then P, inverse, if not P then not Q, and contrapositive, if not Q then not P. Example, find the converse, the inverse, and the contrapositive of the statement if you live in Atlanta, then you live in Georgia. The statement in the form if P then Q, with P being you live in Atlanta and Q being you live in Georgia. The converse would be if you live in Georgia, then you live in Atlanta, which is if Q then P. Inverse is if you don't live in Atlanta, then you don't live in Georgia. Which is if not P, then not Q. And contrapositive is if you don't live in Georgia, then you don't live in Atlanta. If not Q, then not P. We can also use a Venn diagram to assume whether a statement is true or false. We need to assume that the following statement is true. If Jenny lives in Atlanta, then Jenny must live in Georgia. All the people who live in Georgia are represented by the points on the larger circle and its interior. All the people in Atlanta are represented by the points on the small circle. These. Notice that every person in the set A, including Jenny, is also in the set G. The Venn diagram for this conditional statement may be used to test whether its converse, inverse, and contrapositive are true or false. Converse, if Jenny lives in Georgia, then she must live in Atlanta. This statement is not necessarily true, since that point J can still be in G, even though it's not in A. In general, the converse of a conditional statement is not necessarily true. Try a similar argument with the same Venn diagram. Contrapositive, if Jenny does not live in Georgia, then she does not live in Atlanta. Since Jenny does not live in Georgia, she's outside the circle and she's not inside the A, so that means that the statement is true. Theorem 3. If a conditional statement is true, then the contrapositive of the statement is true. If P then Q is true, then if not Q, then not P is true. A statement and its contrapositive are logically equivalent. Chains of reasoning. Each proof that you do involves a series of steps in a logical sequence. In many cases, the sequence will take the following form. If P, Q, and Q are, then P are. This is called the chain rule, a series of conditional statements, so connected is known as the chain of reasoning. Example, if we accept the two statements, if you study hard, then you will earn a good grade, P then Q. If you earn a good grade, then your family will be happy, Q then R, then we can conclude that P to R. That is, if you study hard, then your family will be happy. Problem 1. Write the converse, the inverse, and the contrapositive of the following true statement. If two angles are right angles, then they are congruent. The converse would be if two angles are congruent, then they are right angles. The converse is false because if two angles are congruent, they can have a measure that is not 90. The inverse is if two angles are not right angles, then they are not congruent. This is also false because there can be congruent angles that are not right angles. Contrapositive, if two angles are not congruent, then they are not right angles. The contrapositive is true because all right angles are congruent.